Okay. So, um, well, okay. So first of all, it's not. This is not really the camera angle I was looking for our game. I wanted our game to be more of a fixed perspective, top-down sort of ordeal. So we should probably fix that. Make, we could like add a camera to the car to make like a third-person game. Like if this was supposed to be like a third-person racing game, we could just add a camera here. Like the camera's like 10 times the size. It's like eating up the car. It's like it's like fucking shit. So we could add a camera to this. Like aim it down a little bit. Oops. So now when I possess, okay, so now we have like a bottom, like a behind the shoulder sort of, or behind the back, I guess, sort of perspective. But I wanted this to be fixed perspective, so I don't want the camera to actually follow the car at all. I want the camera to be sort of a different perspective altogether. I don't want it to be attached to the car. So how does one do that? Well, first of all, we need a camera, so I'll just add a camera to the world. So instead of adding it to the actor, I'm just gonna search camera, and here is a camera actor, so I'll just add that to the world. Let's put that in there. I'll pick a perspective that I think is nice. I can look in this little preview here to see what my perspective is currently. So I'll do something like that perhaps. Yeah, it looks pretty good. So how do I make this my actual camera that we use? Well, I'll go into our level blueprint, and I will get our player controller. So we still get player controller. And then I will just do set view. Set view target with blend. And this will actually not change the position at all. It will just tell the player controller which actor to use as its viewpoint. As you see, it doesn't take a camera, it takes an actor. It takes an actor. So I could put any actor I wanted. I could just place like an empty actor and put that in there. But if I use a camera component, then I can set the perspective and I can do field of view and stuff like that. But technically, you don't need a camera; you just need an actor. This will be sort of what the view possession will be, not the actual input possession, but rather where the view will be coming from. So from the new view target, I will just select our camera, or click to get the camera actor reference, and I'll just like pop that in there. I could set blend time. I don't know what blend X means. I don't know what lock outgoing means. Look, I will return the last frame's camera position for the remainder of the blend. Oh, okay. It means when it's blending, it shouldn't. Okay, yeah, okay, I get it. We're not gonna blend though, so it's like ignore these.
What does blend mean in this case?
Well, blending means, if we're going, let's say we wanted to go from the camera perspective here.
Yeah.
Up to, we want to change the camera perspective to be this like up view here. Well, if we just set the camera perspective, we will get a pop, right? We'll be like from here, and then all of a sudden, like in one frame, pop to be up here. Which sometimes you want, sometimes you don't. In It Takes Two, for example, when you go into a trigger to play a cutscene, usually you want to blend into the cutscene. You don't want to pop into the cutscene. You want the camera to sort of move to where it should be over a few frames or a few seconds or something. And that's what a camera blend is. So a camera blend is how it should move from one point of view to the other.
Right, so it's a lerp, basically. Right?
What do you say?
Lerp. It's cool.
Essentially a lerp.
What is the control of that? Can you do like Bezier curves or like?
It seems like though. So you have linear, which is just like it will just linearly go from one A to B. Then with cubic. I don't know.
Nice.
Easy in, easy out, easy in out. So you can select these.
Cool.
So that's cool. I have not worked with this at all. Like at Hazelight, we have our very own camera system. So We don't use this, but it's probably good. I don't know what the XSplit means though. I don't know. Let's just play with that. But yeah, so
Quick question: which blueprint did you do the possess thing in?
level blueprints.
Level blueprint. Okay, nice.
Yes. So, cool. So now if I play, cool. So now we have this fixed camera perspective. So even though the player is possessed in this pawn here, we still have this overview camera. I don't know what we have, why we have letter bars though. Why do we have this? Is that like a setting on the thing? Oh, constraint is pretty. I think there we go. I'll turn that off. There we go. Alright. So now we have this fixed perspective. Cool. But I think we should make our game like 200% more fun by actually making the car move. Because now, yeah, it doesn't move at all. So we should probably fix that. So I'll go in and add some input first thing. So I'll just go into input settings. And I'll add like throttle should be one. So I'll set the W and S, and I'll also add some gamepad mappings right away, because that's probably going to be important if we want multiplayer. So I'll just do gamepad Y-axis. No, actually, now I'll do the right trigger. There we go. So right trigger axis is going to be our throttling. And to back up, if we want to back, then we should probably do left axis. So I'll just do left axis like that. I'll do -1 here. Sorry guys, I have to take this. Sorry, I'm getting a call. Give me 1 second. I'll be right back. There we go. Apologies. So when we do left trigger, we want to back up. So I'm just gonna do -1 as a scale for that one. And then same thing if with S on the keyboard, we're gonna back up. So I'll do a -1 on that as well. There we go. So that's our throttle input, and then we want to have our turn input. And as always, we want to name it some sort of direction. So I'll do turn right. A positive value of turn right is going to mean we're turning to the right. So I'll just do D and A, and then the I'll do the x-axis on the... Hello? Come on. There we go. So D is right, and then A is negative right, so -1. There we go. So that's our inputs. Very cool. Very cool. So to bind this on our car, it's exactly the same as with our player controller. Or not our player controller, our player in our last game. We just override this setup player, input components. So you just override that function. And that's where we set up all the bindings and bind them to functions and so on.
How is it different from beginner play? Or is that because you get the input components into the method? Or
yeah, the problem is that input components, it's weird. I sort of researched this a little bit yesterday, but it's kind of weird when the input component actually is created. And it's not like any other component that is sort of exists on the actor. It's sort of created like midway through, so it doesn't actually exist in begin play, and it doesn't exist like in the constructor. That's why it was kind of weird to set up input from an actor, because you didn't have this like setup player input component function. So it's kind of hard to get like access to the input components, and I'm not 100% sure exactly how it works or why. But with the pawn, at least you get this nice function that you can override. So I don't know. I'm not quite sure.
Cool.
So I will just why can't I fucking, why is it working like sometimes to like create the definition? Whatever. Oh, so I create the definition. So I will bind up the axes, the axi. So we will do add axis, bind axis. So we want this function. So bind axis f name axis name. So we'll do text throttle, and we'll bind that to just a function called race car. Oops, handle throttle input. There we go. And then I'll bind turn right to handle turn right input. You don't need the column handle, by the way. I like the column handle. That's what I usually call my like responses to delegate functions. But yeah, it's you can call them whatever you want. I can tell you right now that that's not at all even close to consistent at Hazelight. What we call like callback functions. Handle throttle input, throttle, handle turn right input, turn right. That's a really bad name for a variable. Maybe I should just do value actually. Maybe I think value is gonna be like way more it's descriptive of what it actually does. What it means. There we go. Come on, I just want to make the signature. Panic.
Gets wider. It'll be better.
No,
I promise.
no, never. I refuse. I love Visual Studio. Okay.
Notepad++.
So yeah, when we get throttle input, we want to move the car. So for now, we'll just do it in here. Probably later we want to do it in tick or something. But let's just, to get stuff working, I'm just going to do the throttle input here. So I'll do add actor world offset. So I'll just move it in the... I'll just make an f vector. So I'll do f vector value times... times times some speed. It's 200. It's probably good. There we go. Let's do. God, it's so slow. There we go. God, that was painful making that. Okay, what's the problem here? What am I missing? Anyone?
You're missing forward vector.
Forward vector. Yeah, that's a
was
good point. We're missing forward vector. Because now it's gonna move in the world X direction. We could fix that by doing the timesing it by the forward vector of the actor. I'm actually gonna do something else. I'm actually gonna do add actor local offsets. Whoops. So that will sort of do that for us. It will transform this vector into local space and move it in that direction. So that's another way of doing the same thing. Either we do forward vector times, or we just do this add actor local offset.
You're also missing delta time, I guess?
Yes, that was what I was looking for. We're missing delta time. We don't have delta time in this function, because it's not tick. We can easily just get the delta time by looking into the world. So I just do get world. And in the world, we can fetch delta time seconds. So if we just want to get delta time from somewhere that's not tick, then we can just peek inside the world and we can get it there. Cool. So let's see what happens. What's the best thing about Switzerland? I don't know, but the flag is a big plus. Okay, so that's pretty funny. Thank you.
That is funny. Haha.
It's pretty good.
All right, so look at that. We have we're rapidly approaching a video game. So you can move forwards, backwards. Amazing. So let's add turning as well. So when we turn, or when we hit the turn input, we want to rotate the thing. So I'll use to add actor world rotation. So I'll make a rotator. And as a quiz, which axis do we want to turn in? Like which Euler axis?
Is it said? Should be.
Yeah, what is that called? What do you call like the up? In the Euler angle terms.
Is it yaw?
Yes, it's the yaw. So let's look. Okay, so I have pitch, yaw, and then roll. So we want to enter in the yaw here. So we want to yaw the car. So I'll just do 0 for pitch. And then for yaw, we'll do value times however fast we want to turn the car. I guess 90. Yeah, 90 per second seems good to me. And then 0. Of course, we got a good delta time in here as well. So we'll get worlds. Delta time seconds. There we go. So now we're gonna yaw the car when we turn right. I invented a new word, plagiarism. Okay, cool. So that's funny. Hey, okay, cool. So now we can turn the car. I think it's a pretty good racing game. Like, I'm having pretty fun right now. If you're gonna go full screen, you hit F11. So with F11, you're going full screen, and it's 10 times more immersive. So yeah, here's the car. So let's say we want to add a second player to this, because I'm pretty lonely guy. So let's just copy the car then. So I'll use Alt drag. So if I hold Alt and drag, I copy the car. And then I'll use the auto possess player 1 instead. So instead of player 0, I'll add auto possess player 1. What will happen now? So if I play, then okay, so I'm still controlling the top one, so that makes sense. That's what I expected. And let's use the gamepad then. So I'll throttle with the gamepad. And unfortunately, I'm still controlling the top car. If I had another gamepad, which maybe I'll go grab it or something, that will actually get assigned to the second player. But by default, the first gamepad gets assigned to the first player, so that every player has a gamepad. If you have two gamepads, that's fine. You just use the second one. But if you only have one, like I do, you can just go into project settings, search for gamepad, and you can do the skip assigning gamepad to player 1. So this will mean that player 1 will only be able to play with keyboard. They won't have a gamepad assigned to them. So that's good if you're trying to do multiplayer games with only one gamepad in your computer. So now if I play, it's still assigning the gamepad to player 1. This might be because we don't have a player 2. So we actually have to tell the game to make 2 players. It only actually creates 1 player by default. So I just go into level blueprints. I'll just add another player. So I just call add player. Create player. Create player. So this will add another player to the game. So we can choose we can choose a player controller ID. If we specify -1, it will just create one and give the first controller that's free. Or we can just type in 1. I'm just gonna type in 1. I don't know what happens if there already is a player assigned to 1. I think it will just do nothing. So yeah, I'll just say controller ID 1. We want to create that player.
Why do we need to create a player but only once if we have 2 players? Like so we have 2 players, right?
Yes.
We only call create player once.
Well, the first player is always implicitly created.
Oh, okay.
So there's always at least 1 player in a game.
Right.
So for every other player, you have to create those manually.
Okay, cool.
So now if we play... Okay, so now it's split screen, so that's not exactly what we wanted, but okay. So I move this with the controller, and hopefully with the stick... Yes, okay, cool. So now I'm actually moving the second player with the gamepad. So if I hit with the gamepad, moving the second player, control or keyboard, I'm moving the first player. But we don't want this split screen nonsense. I want to have just 1 screen. So I'm just going to go in and disable split screen. So I'm just going to do split screen in project settings. At least uncheck this use split screen here. So only I have one screen. There we go. And then I will use the first player screen as like the screen. So the camera angle will be preserved.
Could you quickly show again where you disabled so that the keyboard always, when you separated the controllers in the project settings?
Yes. Oops.
Where was that now again?
It's in skip assigning gamepad to player 1. So that gamepad 1 will be assigned to player 2.
Thank you.
All right. So I don't know about you, but this is not a very fun racing game. Like, you know, it doesn't really work like I expected to. You don't have any momentum. If I stop hitting the key, I stop. Like dead in my tracks. So I thought we'd make it a little bit more physically based. Like we'll make some sort of simulation. It won't be accurate, like it won't be like an actual car, like it won't be Rocket League. But it will be something. So it will be a little bit of physics programming, a little bit of collision programming, which is fun. I enjoy it a lot. And I think it's very useful to learn because almost every game has some sort of, you know, movement or, you know, hopefully a bit physically based programming. Like almost every level in It Takes Two has some sort of physically based system going on in it. And they're very fun to make, and I enjoy it a lot, so that's why I want to do that. So I'll make it like we can collide into walls, and we like bounce off, and we can like drift maybe. Drifting will be pretty cool to do. So yeah, we'll take it 1 step at a time. I think to begin, maybe the first step to do is that we don't just stop dead in our tracks. I think it would make more sense if we accelerate, and then we sort of slowly come to a standstill as we release the accelerate button. So let's do that. So I will actually split it up. So instead of moving the car inside of these input functions, I'm gonna make a tick function. So I'll make it so in tick we're gonna do all of the movement logic. There we go. Now it works. Okay, cool. And I will add a vector to represent our our inputs. What should we call it? Like, yeah, I guess like we should call it inputs. At least make the floats.
Velocity?
At least make the floats. At least the throttle input. And turn input. Turn right input. So in these functions, instead of moving, I'll just save the inputs. So I'll just save the throttle inputs in here. This value. And I'll save the turn right input. So turn right input. This value. There we go. So I'm saving those two so that I can use them later. So let's just make sure it works. In tick, I will just do this essentially the same thing. I'll just do add actor local offset. Let's do F vector forward vector times. We can do this as well. So this is like a static forward vector. This is just like x1 is defined as the forward vector. So I'll use that instead of doing the other way. Times throttle input times 200 times delta time. Just to make sure it works. Compile, read joke.
You didn't activate the primary tick nor the super tick, right?
You
So it's not
interrupted
gonna
my
actually-
joke to give me
Sorry.
great advice. And that's exactly right. We didn't do primary actor tick. Can ever tick. Very good.
But don't you set that in the begin play?
No.
Then I remember incorrectly.
I don't think so. I don't think I've ever done it in. Maybe I'm wrong. I'm pretty sure you do it in the constructor. That feels like a constructory thing to do. We'll
Doesn't
see. Maybe
have
I'll look
to.
stupid. Maybe I'll look
But
stupid.
you can.
I think you can do it also in like the begin play and update, but that's like a method call, right? Not the variable.
Yeah, you
Doesn't
can do like
matter
set
where you
actor
do
tick
it,
enabled.
But you usually do it in the constructor.
Let's see what happens. I'm so nervous. Okay, it works. Cool. So now we're instead moving in tick instead of doing it in the actual input functions. Cool. So then we're rapidly becoming cool. So let's become even more cool by doing what Oliver said is make a velocity. Oh, we're fucking physics programmers right now. Have you guys had your physics course?
Nope. Not
Well,
yet.
you won't need it after this, I'll tell you that. Yes, you will. This will not be. It won't be physics. So, so anyways. So now we want to add an acceleration instead of just manually moving the car. So we are gonna, I am going to add a acceleration force here. And our acceleration is gonna be our throttle input times 200. Yeah. Whoops. So instead of moving the car by this amount, we're just gonna accelerate by that amount, and I'll add it in the actor. Now I will do it actually in world space, so I will do get actor forward vector. So we're gonna have the velocity be in world space. So that means I'm gonna make the acceleration also in world space. So that's our force, our acceleration force. So I will just add that to the velocity. So I will do velocity plus equals acceleration times delta time. So now we're applying our force, our acceleration force, to our velocity. And what I'll do then is I'll move the car by the velocity. So I'll do add actor world offset, because again, the velocity is going to be in world space. So I'll add velocity times delta time. There we go. So now we split up. So we apply our throttle as an acceleration to our velocity, and then we add a velocity to the world offset. So we sort of taken another step in between.
Can I ask why we use delta time 2 times? I thought delta time just needed to be once with the velocity. The acceleration times the delta time.
Well, that's because when we add acceleration, what this means is if we have a 200 of acceleration, right? That means every second we're going 200 speed faster. So every second we want to accelerate by 200 units. So that's what's happening here to the velocity. So that's why every second velocity will be 200 units faster. So that's what this means.
Yes, but it's the one under. I don't really get why we're doing velocity times delta time. I thought acceleration times delta time is enough, or am I wrong?
Well, you have to see this as two discrete actions, right? We are applying an acceleration as one action, and then applying the velocity is a separate action, because then we're asking what is the unit of the velocity. Velocity is units per second as well, right? So if velocity is 200, that means we're going 200 units per second. And to apply...
Oh, and velocity is going to be... Okay. It's gonna add 200 every frame if we don't do times delta time again, right?
Yeah.
Okay,
That means with the acceleration, if we have acceleration of 200, after 1 second, we'll be going at 200 units per second. That's why an acceleration is defined as per second, right? Because we're going 200 units per second, and we're accelerating by that amount per second. That's why it's per second. It's a bit confusing. So after 1 second, we will going at 200 units per second, because that's what the acceleration is. But still, since we're applying it every frame, and we're applying the velocity every frame, we're going at 200 units per second, so we still need to times the velocity by delta time, otherwise we'll be going 200 units per frame. So we still have to convert it to, you know, from per second to per frame. So that's why we have the second delta time. So you can see these two as two discrete actions, and that's why we need the times delta time twice.
Yeah, Philip, I think that's why we had some strange behavior in our game. I missed that part.
Oh. Okay, that may explain it.
Nice.
Yeah, it's easy to miss delta times. So, now if we play and then compile. Did you hear about the mathematician who's afraid of negative numbers? He'll stop at nothing to avoid them. Okay, so that's pretty funny. So when I play now,
Good.
nothing changes. Did I save? I did save. It's time for the restart again. Time for the jokes again. Why do we tell actors to break a leg? Because every play has a cast. I feel like that's like a fact more than a joke. That's like a history lesson. Helvetica and Times New Roman walk into a bar. Get out of here. Shout out to the bartender. We don't serve your type. See, because it's like type, it's like font.
Can I
Like-
try one?
Yeah.
Alright, got something I've heard of before. A farmer has a chicken that is faster than any animal on his farm, the fastest one around. A trader comes by, sees the chicken and wants to buy it off the farmer. He first offers him around $50 for it, but the farmer refuses. Then he goes with 100, still refuses, then 200, 500, 1,000, and now trader realizes it gets ridiculous and asks him, "Why the hell do you not accept amount of money for a simple chicken, dude? What's wrong with you?" Yes, and then he answers, "I want to sell the chicken to you, but it's so fast I can't catch it."
Man, I was focusing on the numbers so much. I was like, okay, so it's like doubling and then it's like tripling. And I was like, that's gonna be the joke, right? It's gonna be a math joke. And then it was like, no, the chicken's just fucking fast. It's just Sonic. That's a good joke though. Thank you. We have fun here. Okay, cool. Okay, so now you can see that it's sort of slowly, as I'm holding the button, I'm accelerating the velocity. And then as I let go, it will just keep going in that direction. So I can actually accelerate like sort of as long as I want, and we just keep going faster and faster. So you know, it's physics. You know, we're reaching something. Fucking physics, guys. There it is. So what do we need? Can I have a guess? Like what component do we need to add to this so we can't just accelerate forever?
Clamp.
I was gonna
We
say
could clamp.
deceleration.
That could be one thing. We could clamp our speed.
Friction.
Friction is another way. Yeah. So yeah, we want to clamp our speed, right? So that's our goal. We want to clamp our speed. And we could, so we can't go as fast as we want. But we also want to be like, if I release the button, after a while we want to come to a stop, right? Because now we're going forever. Like we kind of, if I let go of throttle, I kind of want to go back to 0, right? And in real life, what handles that is something called friction. So friction is the I guess the surfaces rubbing against each other. Here I'm fucking trying to explain friction. Surfaces running against each other, and that produces energy, and that energy gets taken away from the speed, so it comes to a stop. There are multiple ways of doing friction. Friction is like famously impossible to mathematically express. There's no one formula for doing friction. There is something called constant friction, which means that as you're moving across a surface, you're always losing the same amount of speed. So like for every second, you always lose the same amount of velocity. So that's called constant friction. So that would be, we will implement that something like, you know, we will make a friction force. So because friction is a force. So I'll make friction is equal to, so it would be like negative, because the friction always works against the velocity. So it's a force always that's negative to the velocity. So I'll do velocity gets safe normal times some values. This will be like the value of our constant frictions. Let's say 100. We want it to be less than our acceleration. Oops, not all times the time. There we go. So this will be our friction force. So it will be in the negative direction of velocity times 100. So it will always be 100 backwards. So that's going to be our friction. It's going to be a constant friction. So then I'm going to apply that force together with acceleration. So I'll just add those here. So I'll use the acceleration plus friction times delta time. Oops. So now for the velocity, we're applying both acceleration and friction in our equation. Good. So let's see what happens. Let's compile. So when I go, you can see that the car comes to a standstill when I let go. So that's one part fixed. The second problem though is the problem of clamping the speed, right? Because I can still go as fast as I want, because friction will never be stronger than acceleration, right? Since we have a hard-coded 100 for friction, that and our acceleration is 200, that means our friction will never overcome acceleration. Acceleration will always be strongest, which means we will always gain speed. We will always have this net 100 of speed gain. So as I come across the screen now, soon, there it is. We're still going way too fast. Like we can still accelerate as much as we want.
I got a question.
Yep.
Regarding the friction. Cool. I was just curious about here. No, all right. I was just curious because it seemed to me like on friction they would constantly be adding, how you say it, or eventually going to the negative, but no, I just saw the acceleration again.
Yeah, we will never go backwards, because as we start going backwards, because it will be a problem. Like, what if velocity is 0? Like, we will have a sort of a problem then, because then we're getting the normal of a 0 vector. Well, the safe normal will give us like it won't give us like nan. It will actually give us like 1 in the x direction, but even then we should start feeling a little bit uncomfortable. So then we'll start actually like doing negative 0 acceleration when we're standing still. But then as soon as we do that, like, you know, we'll start getting friction in the other direction. So we'll actually start to oscillate back and forth. That's what will happen. So we can probably see that happening if I You can see a little bit of like sort of gyrating a little bit. Enough now. It actually starts. So if I go. I can't really see. You can see that the X value is kind of going crazy here. So it's doing something weird, right? So this way of modeling friction clearly has some drawbacks, right? It's never stronger than acceleration, which is not great. And also, it kind of, the math becomes a bit weird. Because it will always be linear, right? If we look at our curve, so if we draw a curve here for what we're seeing. Oh, excuse me. What? Oh shit. There we go. So here's our graph. So if this is time, right? This is time. And this is velocity. Then what's happening is that since we have a constant acceleration and constant friction, our speed will go up linearly like this, right? Forever. Where the slope of the line is that every second, so if this is 1 second, right? Every second we will be gaining 100 speed. So that's going to be our constant slope of acceleration. And if we let go, so let's say over here we let go of the throttle button, then we're also going to slow down at exactly the same speed. So it's going to be a linear slowdown where we lose 100 speed per second because that's our friction. So, okay, so this definitely works. Like, you know, we are speeding up and we're slowing down. But this is not actually how friction works in real life. Because in real life, or in this case, I should say, we have something called wet friction. So that's another way to model friction, where friction is actually proportional to your velocity. And that kind of makes sense, right? Because, like, if you're a car... Yeah, let me just draw this. So here's the ground. And here's our car. I'm just going to draw it as a cube. Here's our car. Beep, beep. Beep, beep. So here's our car. Copy it. As we're going forward, so this car is going slowly. It's going like that, for example, per second. It's only experiencing friction for this distance here. Over 1 second. You can see the friction as it's going into the little lumps and bumps of the surface. You know, the axle is rubbing against the joints in the car and so on, and it's only experiencing friction for, you know, this amount of distance. Like the wheel is only turning so much, it's only experiencing that amount of friction. But for a car that's going much faster, let's see, it's going this far. This means in 1 second, it is experiencing much more lumps and bumps in the road. So now that the wheels are going into the road more, it's rubbing against it much faster, much more violently. And also, you know, the stuff in the wheels are turning faster, so the axle has much more time to rub against the mechanism in the car, and so on. So there's actually more stuff rubbing against each other as it's going faster. And this is what's called wet friction. So in this case, this car here will actually experience a stronger force of friction backwards. There will be more stuff working against the cars to slow it down than in this slower example. This will actually experience a lower force. And what happens in this case, which is quite nice for our example or for our game, is that in the case of wet friction, there will actually be a point where the car is going fast enough. Let's say it's going that fast. It will go fast enough that the friction will actually match the acceleration. So at some speed, since the acceleration doesn't change, the acceleration is still constant. The acceleration is always pushing the car forwards the same amount. like our engine has not changed. That means since the friction is just growing and growing and growing and growing, actually accelerating, that means at some point the friction is actually gonna match the acceleration. The friction will have grown enough to be as big as the acceleration. So these two will be now equal. And that means the car will stop accelerating. Or it will accelerate, but it will just accelerate with value 0 because the accelerations would just beat each other out. Is wet friction the same as air resistance drag? Yes, it's the same. Because then it's the same thing, you're hitting air molecules. And the more air you travel through, the more air molecules has a chance to hit you in the face. So that means the faster you go, the more stuff is coming in your way. So you're slowing down faster.
I'm assuming this is only true when the acceleration is constant. So if you're driving an actual car and like pushing down the gas pedal more, then I'm assuming you can still go faster.
Yes.
Yeah.
So if you could accelerate more, if you could push down harder, then of course your acceleration will increase. So then you will have to go in faster for the friction to kick in. But yeah, this is the reason why you can't go infinitely fast with cars. Like, at some point friction is gonna beat out your engine. Like, however strong your engine is, there's always gonna be friction to beat that out. So the only way to overcome that is just get a bigger engine. Cool. And what's nice about this as well, and another cool result of this is that our curve actually looks a lot more nicer. It won't be linear anymore. Instead, we'll get a curve that looks something like this. It will start fast because we're experiencing very little friction. So acceleration will be the dominant force. And then as we're going faster and faster, they will start to compete with each other and will actually level out like this. So here acceleration is the dominant force, and as we're going up, then friction becomes equal. And as they're equaling out, then we stop changing our speed. And then as we release the throttle, then all of a sudden the acceleration goes away. So all of a sudden only friction is acting upon us. So we'll actually start decreasing in speed very, very rapidly. And we start to go down slowly like this. And then after a while we sort of level out. So we get this sort of shark fin curve. Quite nice. So that's called wet friction, and it's what we use always, almost always. I've never in my life actually used constant friction because it's weird and it doesn't really apply to almost anything. So I don't know, it's probably useful somewhere. I don't actually know if there is such a thing in nature as constant friction. I don't know if there are. Maybe there is, I don't know. But as far as I know, almost everything in life is wet friction. And of course the mathematics we're gonna use is much more easy than actual wet friction calculations. Don't think that this is like actual physics math. The physics mathematics are way more complicated than we are gonna do, but it's sort of roughly modeled after wet friction. Good enough for us. Let's do 5 minutes, and then after those 5 minutes we'll implement wet friction, and then we'll take lunch. So see you soon.